Recording in progress.
Ça te va si je me mets au bord? Je vais devoir me lever. C'est toi le plus long, c'est toi qui crois.
J'en ai peur.
Pouvoir placer les lobes du ouais. Ok.
So it's 9:30. Yeah, yeah. Okay.
Voilà, mesdames, messieurs, bonjour, bienvenue pour cette soutenance de thèse. C'est un grand plaisir pour moi de présider au nom de l'Université Paul-Sabatier, de vous accueillir et de présider ce jury. Je suis Jean-Philippe Thiran, je suis professeur à l'École polytechnique fédérale de Lausanne et désigné volontaire pour présider cette soutenance de thèse de Sayantan DUTTA. Welcome to you, very welcome.
Thank you.
Welcome to your family online and to the people attending online as well. As you understand, I will use a bit of English and a bit of French. So it's first my pleasure to introduce the jury. I will start by introducing the jury. Donc, je vais commencer par présenter le jury, en commençant par les deux rapporteurs. Alors, les deux rapporteurs sont le professeur Steve McLaughlin de Heriot-Watt University in Edinburgh, et puis le docteur Pierre Borgna, directeur de recherche CNRS à l'École normale supérieure de Lyon. Les deux examinateurs sont Dr Laure Blanc-Ferraud, directrice de recherche CNRS à l'Université Côte d'Azur, Sophie en Toulouse, et moi-même. Et les co-encadrants, le directeur de thèse est le professeur Adrian Bassarab de l'Université de Lyon et laboratoire Creatis, bienvenue Adrian. Le docteur Bertrand Georgeot, directeur de recherche CNRS au laboratoire de physique théorique de l'Université Paul-Sabatier, bienvenue. Et le professeur Denis Kwame de l'Université Paul-Sabatier. Voilà, that's the introduction. So now the floor is yours for your presentation for about 45 minutes.
Okay.
And then we'll take questions from the jury and from the audience if you wish. Okay, so the floor is yours.
Yeah. Thank you. So, hello everyone. Good morning. So, I am Sayantan DUTTA. Today, I will present a few results from my PhD thesis. So, which is supervised by Adrian Bassarab, Bertrand Georgeot, and Denis Kwame at University Paul-Sabatier, here in Toulouse, in the university, in this elite and the theoretical physics lab LPT. So the title of my presentation is Novel Prospects of Image Restoration Inspired by Concepts of Quantum Mechanics. So for my today's talk, so this is the outline of my today's presentation. So I will start by the motivation of this PhD work. Then I will briefly present some basic ideas and basic principles of quantum mechanics, which are useful for this work. Then I will discuss some existing literature. Then from section 4 to section 6, I will present a few of my results and few of my contributions, then finally draw the conclusion in section 7 and discuss the future possibilities at the end. So this is for the today's outline. So let's start by the motivation. So as we know, the image restoration problem can be mathematically formulated by using this expression y equal to n of ox, where y equal to n of ox, where y is the observed degraded image, n is the effect of the noise, O is the degradation operator, and x is the underlying hidden image. So the objective is to estimate this underlying hidden image x from this degraded observation y. Now, depending on the degradation operator O, we can have different type of image restoration problem. For example, if O is an identity operator, then it becomes a denoising problem. If O is a blurring operator, then we have to solve the deconvolution or deblurring problem. And if O is a product of subsampling and the blurring operator, then we have to tackle the super resolution problem. Now, till today, we actually use standard or traditional approaches and classical computers for solving all this restoration problem. But after the discovery of quantum mechanics, especially the quantum computation in 1980s, it becomes very clear that the future will be an age of quantum computers, where we will have these quantum algorithms, and using quantum algorithms and quantum computers, we can solve very efficiently these real-life problems compared to a classical one. But till today, the quantum computers we have, these are very small in size, so the scope of implementation of real-life problem is very limited. But there is another possibility, that is designing an algorithm inspired by the quantum mechanical principles, but these algorithms are designed for the classical computers. So in my PhD, I focus on this aspect of designing algorithms which are powered by quantum mechanical principles, but works on a classical computer. So by doing that, our algorithms get all the benefits from some quantum mechanical principles, and which makes them more efficient compared to the traditional approaches. So we want to study this domain in my PhD work. So next, before going to more details, let's discuss some basic ideas of quantum mechanics which are useful. So let's start by the classical picture. Now, in classical mechanics, we can precisely determine the position and momentum of a classical particle like this. Now, here we have a classical particle, and this particle is moving under this potential surface V. So V is the potential, and the E is the total energy of this classical particle. That means the sum of the kinetic energy and the potential energy. Now, in this classical picture, since the total energy of this classical particle is much less than the potential barrier here, so this classical particle will never able to cross this potential barrier and will never reach this place. So this particle will always trapped in between this region and oscillate forever if there is no damping effect. Now, this is the classical picture. Now, in a quantum mechanics, we have a different perspective of this viewpoint. In a quantum mechanics, actually, we cannot precisely determine the position of a quantum particle. Instead of that, we have a probabilistic distribution, and which is given by the wave function psi. And so this wave function and the probability of presence of this quantum particle at some point is given by the mod psi square. And so here we have a quantum particle with same energy level E, the total energy E. Now, and the probability and the characterization of this quantum particle is given by the wave function psi. So this is psi is the wave function. Now, this wave function psi is actually solutions of the Schrodinger equation. So this is the Schrodinger equation, where h bar is the Planck constant, m is the mass of the quantum particle, this nabla is the gradient operator, psi is the wave function, as I told, and v is the potential surface, the potentials of the system, and E is the total energy of the quantum particle. Now, let's have a look of some particular example. So if we have a constant potential here, and if we put this constant potential in the Schrodinger equation, and then solve the Schrodinger equation for different energy level, we will get different wave functions for every energy level. So you can see that the frequency of the wave function increases with increasing energy value. But for a particular energy level, the frequency of the wave function is constant. It does not vary. And this is because the frequency of the wave function depends on this factor, E minus V. Now, since we have a constant frequency, you have a constant potential, so the E minus V for a particular energy level is fixed. So that's why you have a constant frequency for this constant potential. Now, if we have a different potential, if we have potential with two different heights, so here we have a low potential region, and here we have high potential region. Now if we solve the same Schrodinger equation for this new potential V and for the same energy level E0, E1, E2, E3, and E3, so we will have a different set of wave function. And here we can see that the frequency of the wave function is not constant anymore. Instead of that, we have different level of frequency for different region in the space. And particularly, we have very high frequency region in the wave function, which are associated with low potential region. And we have low frequency for the high potential region. And this is a very unique property of this wave function. So you can see that these wave functions are using different level of frequency to probe different region in the space. And in our work, we will exploit this property. Next, there is another property called quantum localization effect. Now let's consider the same potential V, but now instead of having a smooth potential like before, we have a random noise here. So the potential is random here. There is random noise in the potential. Now, in this random noise, due to this random noise, the wave function is not spread over the whole space. Instead of that, the wave function actually exponentially localized into a particular region in the space. And this effect is called localization. And if we increase the noise level, these wave functions become more and more localized. So this property is called the quantum localization effect. And this is because of this random noise in the system. So in our work, we also need to tackle this type of localization problem while designing our algorithm. So these are some basic principles that we need to know before going to our work. So first, I will discuss some existing literature on this aspect. So some initial work was proposed by Juanina Elder, where she proposed a quantum measurement idea for signal processing. Then Gabush and co-authors proposed an idea of an object segmentation or object detection by using the quantum tunneling effect. Then there is a series of papers by Akram and his co-authors for image segmentation and detection, where they use these wave functions for object detection problem. Next, there is another group where they try to do signal denoising using this discrete spectrum of Schrodinger operator. And further, they extend this work for the image representation as well, using solving the problem in a column and row-wise fashion, using this discrete spectrum of Schrodinger operator. And they apply, and the same group applied the same method for real medical imaging problem as well. So these are the most significant work in this domain. So you can see that there are not many works actually, not many works has been done till today. So that is also a big motivation for us to explore this field in a more detailed way and try to explore other possibilities. So now I will move to my contributions. So first, I will discuss how to construct an adaptive transformation using the solutions of the Schrodinger equation. So our first idea is to construct an adaptive basis vector by using the solutions of the Schrodinger equation. So this is the Schrodinger equation, and we can rewrite the Schrodinger equation in an eigenvalue problem, H psi equal to E psi, where H is the Hamiltonian operator. Now, the idea is to replace this potential V by the image pixels value. That means the image, the 2D image acts like a 2D potential surface. That means low pixel value or the black region in the image acts as a low potential region, and higher potential or the bright region in the image acts like a high potential region. And an imaginary quantum particle is moving around this potential surface. So this is the idea. Now, since images are discrete in nature, so after the discretization of the Hamiltonian operator using these image pixels as a potential, we get this discretized Hamiltonian operator, and the set of eigenvectors corresponding to this Hamiltonian operator gives us the adaptive transformation. So now let's have a look how this adaptive vectors looks like in presence of noise and without noise. So for this, I took a standard image, this boat image, where half of the image is contaminated by noise, Gaussian noise, and half of the image is clean. So I extract two patches from these two sections of the image. One is noisy patch, one is clean patch. So you can see that the two patches are more or less have similar type of patterns in them. And so this is the 3D surface plot of these respective 2D patches. So we can, here the Z direction represents the pixel intensity. So you can see, so we have high pixels value, which are the higher potential region or the red region in the image, and the low pixels value is the blue region, which is the darker region with the darker pixel value. So we can see there are many hills and valleys in these potential surfaces. So we use this potential surface in the Schrodinger equation and solve the Schrodinger equation for the energy level E in both cases. And from the solution, so this is the respective wave function for the energy level E under this potential surface. And this is the 2D contour plot of these respective 3D wave functions for both cases. Now for the clean image patch, we can see that we have different level of frequency throughout the space. So for example, we have a high frequency region here, which is associated with the low pixel value or the low potential region. And also we have low frequency region, which is associated with higher potential value or higher pixels in the image. So we can see that our wave functions uses different level of frequency to probe different pixel value in the image. So that is a very unique property of our wave functions. And on the other hand, in presence of noise, we can see that the wave function is not spread over the whole space. Instead of that, the wave function exponentially localized into a particular region in the space, and this is because of the quantum localization effect. And this type of localized wave function are not actually very useful for image denoising or image decomposition problem. So while designing image denoising algorithm, so we have to tackle this localization problem to get a high quality result. So for this, we propose this denoising pipeline. So initially we have a noisy image Y. Then we apply a Gaussian smoothing to compute YB from this noisy image Y, just to counter the localization effect. Then using this YB, we construct the Hamiltonian operator H. Then from the Hamiltonian operator, we calculate the eigenvectors. And from these eigenvectors, we get the adaptive basis vector. Now we project the original noisy image Y on this adaptive basis vector to compute the projection coefficient. So that means we just perform this initial smoothing just to counter the localization effect. And then from this smooth image, we compute the adaptive basis vector. Then we project the original noisy image on this adaptive basis vector to compute the projection coefficient. So next is simple. So we just perform thresholding, then do the inverse transformation and get the denoised image. So this is the denoising pipeline here. Now here I show some result for the denoising performance, which is an average result over 7 standard images and for 3 different noise statistics, Gaussian, Poissonian, and speckle. So this is the average value for total 21 images. So average PSNR data. So, and our method is known as QAB, quantum adaptive basis. And here I show comparison with some standard image denoising techniques, for example, wavelet, hard and soft thresholding, dictionary learning, and total variation-based method. So here we can see that our QAB can significantly outperform the standard techniques for image denoising for different type of noise statistics. So which justify that our QAB algorithm is very efficient to adapt with different type of images and different type of noise statistics. So this is the initial result. But so we can see that our QAB algorithm has a good denoising performance and also it is very flexible with respect to noise statistics. So these are the very good point, but there is some serious point of concern. First of all, the high computational cost of the eigenvectors from the Hamiltonian operator. Next, if we have a very large image, we cannot process the whole image at a time. So we divide the image into small blocks and process them independently. Now in this construction, so all the blocks are processed independently. So we are not considering the path similarity between these two blocks, between the neighboring blocks. So which is a very fundamental property or a key ingredient for medical images or real images. So that property is missing here. Next, actually we are performing this Gaussian smoothing to escape from this localization effect, which is also a limitation for our proposed algorithm, because we need to tune the respective hyperparameter which is associated with this Gaussian smoothing, so which just increases our computational complexity, so which is a serious drawback in our algorithm right now. Now to escape from this limitation, we further generalize our idea using quantum many-body theory. And so in the next section, I will discuss how to resolve this issue using the many-body framework. So now let's move to the next section. So till now, I was actually discussing this one-body quantum system. That means in our quantum system, there is only one quantum particle. And based on this one-body system, we are performing all this computation. So this is the Schrodinger equation for the one body system, as I just told before. So H psi equal to E psi, where A represents the particle, the quantum particle or the patch A for the image processing point of view. Now here AJ is the Hamiltonian operator. So this is the Hamiltonian operator, just as I showed before. So, and here our idea is to replace this potential V by the image pixels value to calculate the eigenvectors. And then from this Hamiltonian operator, we get the eigenvectors, and which gives us the adaptive transformation. So this is the one body picture. Now, if we have more than one quantum particle in the system, that means if it is a many body system, then there is a particle to particle interactions takes place. And as a consequence, in this many body framework, we have an extra term in the Hamiltonian operator, and which is the interactions term, which reflects the interaction between the neighboring particles. Now, for an image processing point of view, we divide the whole image into small patches, where every individual patch acts like a single particle system, and as a whole, they behave like a many body system. And in this many body construction, this interactions term actually preserves the structural similarity in a local image neighborhood. Now, after constructing this new modified Hamiltonian operator for this many body theory, we calculate the respective eigenvectors AJ from respective eigenvectors from this Hamiltonian operator AJ, and which gives us the adaptive transformation for the patch A. So this is the idea. So we repeat this step for every individual patch to calculate their respective eigenvectors. Now let's have a look how this construction works. So we have a noisy image that you want to denoise. So first we choose a target patch. So we want to denoise this one first. So centering this target patch, we choose a search window, then extract all the patches from the search window. So here the patches can overlap. So this is the target patch, and this is the respective neighboring patches around this target patch. So we calculate the interactions between these two, between them. So target patch and its neighboring patches. So this is the interactions term, and combining all the interactions, we get the total interaction. And then finally add the target patch with the total interaction, we get the effective potential. So this is the modified potential now. And so this is the modified potential in the 2D plot, in the pixel wise, this jet representation. So this is the modified potential for this target patch, this one, this red one. Now we use this modified potential in the Hamiltonian operator to calculate the respective eigenvectors. Now here I just wanted to give you the reminder that we still have the property that the wave function will use different level of frequency for different pixel value. So it will use high frequency for the low potential or low pixel value, and it will use low frequency for the high pixel value or high potential region. Now, how to calculate these interactions between the target patch and the neighboring patches? So for this, we also get inspiration from physics, the power law in physics, and we propose this interaction idea. So if we have two patch A and B with pixel value A1, A2, A3, A4, and B1, B2, B3, B4, and if the distance between these two patches are DAB, which is the real distance or the Euclidean distance, then the interactions term actually linearly proportional with their absolute value of pixel-wise difference, and also it is inversely proportional with the square of the real distance or the Euclidean distance. And here P is the proportionality constant, which is a hyperparameter for the image processing point of view. So how does it work? So if the distance between the patch A and B is very small, that means if two patches are neighboring patches, then if A and B, they are very similar, that means their pixels value are very similar, then they will show low interaction, because the distance is also low and their pixel-wise difference is also very low. So their interaction term will be very low. On the other hand, if A and B are very different from each other, that means if their pixels value are very different, then this term will be very large. So their interaction term will be very high. On the other hand, if the distance between the two patches are very large, if they are very far from each other in the image, so despite their similarity or dissimilarity pixel-wise, so their interaction term is always low, will be always low. So, and this is because this distance is in the denominator, so it is very large. So it does not depend on the pixel-wise difference anymore. So it is always low for the far placed patches. So you can see that this interactions term actually shows high interactions for neighboring patches if two patches are very different from each other, and shows low interactions if two patches are very similar, pixel-wise very similar. On the other hand, if two patches are very far from each other, they always show low interaction. So by doing this interaction term, we can actually preserve the structural similarity in a local image neighborhood by using this interaction term quite efficiently. So this is our idea for considering of calculating the interaction term. Now, by doing that, we study the denoising performance using our proposed algorithm, which is known as DQUIP, or denoising by quantum interactive patches. And we also study the Gaussian and the Poissonian denoising problem using our DQUIP algorithm, and compare with state-of-the-art method like non-local mean-based method, graph signal processing, dictionary learning, and BM3D, and also compare with our single particle-based QAB algorithm. Now, here I show results for the Gaussian denoising problem. So we can, and here the best value are highlighted in red. So we can see that the DQUIP and our, so this is our DQUIP algorithm, our result. And this is the BM3D algorithm. So you can see that the BM3D and the DQUIP is the best two performing method for all the images from low to high level of noise. Also, I just wanted to highlight one more thing. So this is our single particle-based QAB algorithm, which in the first section what I proposed. So we can see that there is a significant improvement in terms of PSNR, especially in terms of SSIM in our DQUIP algorithm. And this is because of the consideration of the interaction term, because it can efficiently preserve the structural similarity in a local image neighborhood. That's why you have a higher SSIM value compared to the QAB algorithm. And I also wanted to show the Poissonian denoising result as well. So we can draw the same conclusion here as well. So so this is the BM3D algorithm, which is customized for Poissonian denoising problem. So you can see that this BM3D based method and our DQUIP is the best two performing method here as well, compared to this non-local. So this is the non-local mean-based method for the Poissonian denoising problem. And here I show two visual results for the Gaussian. BM3D and our DQUIP is the best two performing method. So I just show the results only for these two methods here. So we can see for the Poissonian denoising problem, so we have a very high level of noise, SNR equal to 2 dB. And we can see the DQUIP algorithm performs quite efficiently for removing the noise from this high contamination. And also for the Gaussian denoising problem, we have a SNR equal to 16 dB. And we can see that DQUIP slightly outperform BM3D in this case, and efficiently recover the denoised image, and while preserving the structure of the house and everything. So we can see that visually, we can also see that our DQUIP algorithm performs quite efficiently for Gaussian and the Poissonian denoising problem. Next, we also study the ultrasound image despeckling problem using our DQUIP algorithm. So actually, ultrasound images is a very important image modality for medical imaging. And but during the acquisition process, these ultrasound images generally get contaminated with speckle, and which significantly reduces its spatial resolution and quality. And this and that's why it's very difficult for doctors to get a better medical diagnosis. So that's why despeckling is very important to get a high quality image, and which is very important for the medical treatment. Now here we show the ultrasound image despeckling result using our DQUIP algorithm. So this is a medical thyroid image, which is a speckled image, and this is our DQUIP algorithm. The result is by using our DQUIP algorithm, and I show the comparison with anisotropic diffusion, Lie filters, and non-local mean here, non-local means. And on the above, I show the normalized pixel intensity, which is extracted from this red line for all the images. So you can see that the anisotropic diffusion gives the low contrast to noise ratio, but the resolution loss is also very low. And this is also visible from this graph, this blue line, that we can see that the gradient of this blue line is very high compared to other methods. So this is the anisotropic diffusion. So that's why we have a less spatial resolution loss. On the other hand, for the non-local mean, we have a higher contrast to noise ratio. We have a high CNR, but the resolution loss is also very high compared to other methods. And this is visible from this purple line, which is for the non-local means. So we can see that the gradient of this line is much lower than the others. So that's why we have a higher resolution loss here. On the other hand, for our DQUIP algorithm, it gives a good balance between these two. It gives a higher CNR data while having less spatial resolution loss, and which is also visible from this red curve, which is for our decoupe algorithm, we can see that the gradient of this curve is much higher than the local mean, but it is lower than the anisotropic diffusion. That's why we have a higher resolution loss compared to anisotropic diffusion, but much lower resolution loss compared to non-local mean. So we can see that decoupe gives a good balance between these two. So, and it also justifies that our decoupe algorithm is very efficient to adapt with different type of images, even for the medical ultrasound image despeckling problem. So with this decoupe algorithm, we propose a patch-based architecture by adapting the concepts of quantum many-body interaction theory. And since we are working on this patch-based architecture, so the computational cost is also very low compared to the single particle-based theory, since the patch size is very small here. Also, here we do not need to compute any Gaussian smoothing to escape from this localization problem. This is because actually IPR is a metric for the measure of the localization of the wave function. And if the IPR value is greater than the patch size, so then it is not very significant. This localization effect is not very significant for the image denoising or image decomposition problem. Now, since we are working on a small patch size and the IPR value is much greater than the patch size, so we do not need to compute any extra Gaussian smoothing to escape from this effect. So that's why we can directly use our algorithm without performing any Gaussian smoothing. And next, in this many-patched architecture, we are considering this interactions term, which reflect the structural similarity in a local image neighborhood, which significantly preserve the structures. And that's why our algorithm becomes very versatile in nature, and we can easily extend our algorithm for Gaussian denoising and beyond Gaussian denoising, for example, Poissonian denoising, without any modification. And we also show good medical good performance in medical ultrasound image despeckling problem as well, due to this versatile nature of our decoupe algorithm. Furthermore, we also study the super resolution problem for the CBCT images. And in this super resolution problem, we place our decoupe denoiser as a plug and play and the rate prior. And we observe that for this clinical CBCT super resolution problem, our decoupe algorithm acts quite efficiently without any problem and gives us a high quality super resolution data. So we can see there are many advantages of this decoupe algorithm, but there is also a point of concern, that is the choice of the hyperparameter. Because actually we have 3 hyperparameters in this construction, and this choice of this hyperparameter we did by manually tuning them, so which is a computationally very costly. So that is also a limitation for us. So our idea to solve this issue, to extend our model into a CNN-based architecture, where we can solve this parameter tuning problem by using the power of convolution neural network. So in the next section, I will discuss how to do that, how to unfold our decoupe algorithm into a CNN-based framework. So this is the schematic diagram of our decoupe denoiser, which I just discussed. So here we have a noisy image, Y. Then we apply the patch extractor operator to extract all the patches from the image. Then from these extracted patches, we calculate the total interactions L, which is multiplied by the proportionality constant, which is the hyperparameter. And then combine these total interactions with the nabla operator and the original noisy patch to calculate the Hamiltonian operator. And from the Hamiltonian operator, we get the adaptive basis for the respective patches. And then we project the original noisy patch on this adaptive basis to compute the projection coefficient. Then we perform thresholding and then do the inverse transformation and get the denoised image. So this is the decoupe algorithm, which I just discussed before. Now here we have 3 hyperparameters, as I told. So we have the proportionality constant. Then we have this a square by 2m in the nabla operator, which controls the frequency in the frequency of the Hamiltonian frequency of the wave function. Then we have the thresholding energy. Now in our work, we propose some physical intuitions that how to tune them depending on the noise level and the noise statistics. But these parameters are fixed for all the patches in an image. It does not vary in a patch-wise fashion. But since our algorithm has a non-local framework, so it becomes very obvious to tune them separately depending on different patches. But it is almost impossible to tune them by hand for different patches. So that's why we convert our algorithm into a CNN-based architecture where we can solve this parameter tuning problem quite efficiently by using the backpropagation idea. So for this, we propose this deep unfolded network. So this is the Decoupe algorithm, and this is the respective deep unfolded model. So here, the basic idea is just to replace the matrix multiplication by the convolution kernel. So it is the main idea. And then we do then we trained our model in a supervised way. And here, so this is our proposed deep unfolded network. So the first part is same. So we have a noisy image. Then we apply a patch extractor operator to extract all the patches. So it is same for both cases. Then to compute the interactions, so this is the interactions term. To compute the interactions, we perform a convolution layer. So this is, we just replace this matrix multiplication P times L by this convolution layer with a convolution kernel C1 to compute the total interaction. Then we construct a kernel C2 by using this total interaction with the nabla operator and the original noisy patch. And so this is we construct this kernel C2, this is the Hamiltonian kernel, and then use this kernel C2 in the next convolution layer, which replace this matrix multiplication of the computing the projection coefficient. So by performing this next convolution, we are computing the projection coefficient, and then perform the ReLU function for the thresholding. And finally, for the inversion, we use another convolution, which will do the inversion process, which will just replace this B inverse L, B inverse R. And then finally, combining all these patches to their original location, we get the denoised image. So this is our deep unfolded network. Now here, our deep unfolded network actually known as DIVA. And here I show the denoising performance of our DIVA algorithm. So here I show the average result over 5 benchmark data sets. And here we have 235 images in total. And also we have very low to high level of noise from sigma equal to 10 to 100. And I show comparison with state-of-the-art DNCNN and FFDNet network. And I also compare with BM3DNet, which is a deep unfolded version of the BM3D based method. And this is our baseline Decoupe algorithm. And this is the deep unfolded version, the DIVA of our Decoupe algorithm. And here the best results are highlighted in red and the second best in blue. So you can see that the DIVA is the best method in all cases for low to high level of noise in all 5 benchmark data sets. And it outperforms this DNCNN and FFDNet in all cases. So which clearly justify that it is very good for the denoising work. And also we have a significant improvement compared to the Decoupe algorithm as well. So which is the baseline method. So here I also show 2 visual examples. So first one, it's the moderate level of noise, and this is the very high level of noise. And here from the image, we can also see that if we look at the structure around this window here, and if we compare with the DNCNN and FFDNet, we can see the DNCNN and FFDNet is also quite good. Their result is also not very bad, but our method is, in our method, the structure is much better contrast in well preserved compared to the DNCNN and FFDNet. That's why we have a better SSIM data compared to these algorithms. And also our algorithm significantly outperforms this IRCNN and the BM3DNet and Decoupe algorithm, the baseline Decoupe algorithm. And also if we look at the patterns near the eyes of this parrot image, and if we compare with FFDNet and DNCNN, we can see that in our case, the structure is much better and in much better quality compared to these 2 patterns here for these 2 standard state-of-the-art methods. And that's why we have a high PSNR and high SSIM data for our DIVA algorithm. So you can see that visually, we can also see that our DIVA algorithm is very efficient for denoising tasks. Furthermore, we also extend our DIVA algorithm for more general image distortion problem. And for this, we propose this DIVA advanced network. And where the first part of this algorithm is same, so there is no change, but we just increase the depth of our network, where the rest, this last convolution layer actually acts like a neutralization layer to counter this degradation operator. And so the first part is similar, so there is no change. So, and we study this DIVA advanced network for image deblurring, image super resolution, and image imprinting problem. And here I show results for Gaussian deblurring and for an image inpainting problem. So in this image inpainting problem, actually, we have random pixel missing. So 50% pixels are missing here. And I compared with the state-of-the-art IRCNN for the image inpainting problem. And from this F16 logo here, we can see that compared to this IRCNN, our DeFi Advance can efficiently recover the structure from this masked image compared to this benchmark method. And also, if we look at the Gaussian deblurring problem, if we look at the beak of this penguin and the tail of the penguin, we can see that compared to the other benchmark method, so the edges are much sharper compared to this state-of-the-art methods here. And that's why we have a better SSIM and PSNR data here. And also visually, it is clearly it's clearly visible that the edges are much better preserved in our DeFi Advanced network. So you can see that the DeFi Advanced network can also works efficiently for the general image restoration task as well. Furthermore, we also study this. We also apply this DeFi network for ultrasound image enhancement problem. And for this, since we are using a supervised network training, so we use 700 high-resolution human anatomy images, which are extracted from National Library of Medicine, and then trained and then generated these respective 700 speckled image, which are simulated by the Simon's toolbox. And so we have this simulated speckled image from this high-resolution data. And here I show the results on the simulated ultrasound images. So these are the high-resolution human anatomy images, and these are the respective speckled version. So these are the testing data set. And here I show comparison between our Decomposition algorithm and our proposed this DeFi Advanced network. So we can see that it is clearly visible that we have a very high resolution and very high quality image compared to the baseline Decomposition algorithm from the speckled version. So which is clearly visible here. That's why we have the very high PSNR SSIM data compared to this baseline Decomposition algorithm. Furthermore, we also apply the same trained model in more medical ultrasound images. So we apply the same trained model for cardiac ultrasound image enhancement problem. So this is the observed cardiac ultrasound image, which is obtained from a patient during his regular health checkup. And we can see that the observed image is very low in quality, and it is contaminated with speckle, and the resolution is also very low. And on the other hand, this is our enhanced image. So you can see that the speckle is significantly removed from this image, and the image quality is also significantly improved from this low resolution data. Also, this is another example. We can draw the same conclusion here as well, that the structure of the image is well preserved, and also the resolution is enhanced from this low resolution observation, and also the speckle is significantly removed from this ultrasound image, observed degraded ultrasound image. So which clearly justify that our DeFi Advanced network can efficiently work on ultrasound image enhancement problem as well. So finally, let's summarize my work. So first of all, I propose a quantum adaptive transformation by using the solutions of the Schrodinger equation. Then we further generalize our idea using the quantum many body theory, and we use a patch-based architecture. And in this patch-based architecture, these many patch interactions actually preserve the structural similarity in a local image neighborhood. Then, and because of this adaptive nature, our algorithm is very flexible with respect to different noise statistics and different type of images, different level of noise intensity as well. And we also observe that our methods can act quite efficiently for medical ultrasound and CBCT imaging application as well. And we also show that our decouped denoiser or our state-of-the-art denoiser can act quite efficiently as a plug and play and the rate prior in the image super resolution problem or general image restoration problem. Finally, we extend our model into a deep unfolded network where we unfold our baseline algorithm into a CNN-based architecture for general inverse problems. And using this deep unfolded model, we observe that there is a significant improvement in the image restoration task compared to the state-of-the-art techniques. So this is the main conclusion of my work, but there are still many things can be done for the future. So there are many open perspective. I just wanted to highlight few of them. So for example, right now we are actually using the supervised machine learning technique, but for real medical application, unsupervised machine learning technique is very important. So this is an obvious perspective for the future. And we can also try to use other type of loss function instead of using mean square loss, mean square error, because right now we are using mean square error. So we can use perceptual loss function that might be useful for the future. And also we can try to design more complex network architecture and maybe using transformers or attention mechanism to get a more robust network and to get a high quality result. Furthermore, we can also try to incorporate more advanced quantum mechanics based theory. For example, we can try to consider harmonic oscillators like thing and to get a more complex quantum mechanics based architecture. And finally, till now, actually, we are using the time independent Schrodinger equation. But the time dependent Schrodinger equation can also be a possible perspective, because this type of equation can be useful to process periodic signals like periodic signals. So that can be a perspective also. And also just a quantum computing, also a obvious perspective, where we can try to design quantum mechanics, where we can try to design a quantum algorithm for quantum computers, and where these quantum computers are very efficient compared to classical ones. So we can try to design some quantum algorithms based on our proposed principles. So these are some possible perspectives, but there are other perspectives as well. I just wanted to highlight one of them. So this is a very recent publication where they use our quantum mechanics based representation technique. So they actually use our quantum adaptive basis vector to estimate the systemic quality factor. And they use this systemic quality factor for the hydrocarbon detection. So we can see that there are some other application as well. So this is just I just highlight a few of them. So there are many things can be done. So yeah, so this is my list of my publication. So that's all for my presentation. And finally, I just wanted to thank my supervisors for their support and guidance for the last 3 years. And actually it is 3.5 years, starting from my M2 internship. And I also wanted to thank the reporters for reviewing my manuscript and giving me very nice and positive feedback. And wanted to thank all the jury members for coming here today in person, especially. So thank you very much for everything.
Thank you. Thank you for the presentation. Thank you very much for the very good timing as well.
Yeah.
45 minutes. So now let's move to the questions. And I
Yeah.
the first reporter.
So, Sayantan, thank you very much
Yeah.
for a very interesting thesis and a very nice presentation.
Yeah.
And as you'd expect, I have a questions for you.
Yeah.
But I would start at a general level.
Yeah.
So, it's been an interesting